All right, here that we're recording in progress. Okay, so we're up to 7.4. It's on partial fractions. On the calendar, I was scheduled to start 7.4 today. I already snuck in some of it yesterday, so we're a little bit ahead. So Friday, you'll get another quiz. And Friday after that, the 24th, will be our next test on chapter 7. So now that you've already seen one test, you know what they all pretty much are like. They're all the same style. Okay, so the next test will be a chapter 7 test, essentially. Okay. All right, so let's get back to partial fractions. Problem number 11. You go from 0 to 1 of 2 over 2x squared plus 3x plus 1 dx. All right, so the first thing I'm going to do is factor at the bottom. And this factors quite easily into 2x plus 1, x plus 1. The numerator, 2, think of it as 0x plus 2. In case you say, do I have to do that? Yes, in this particular case, you have to do that. Otherwise, it's not going to work the right way. So just go ahead and do it, and you'll see the reason why we do it that way in a little bit later. Right, so 2 over 2x squared plus 1, 2x plus 1, x plus 1. So break it down into a over 2x plus 1 plus b over x minus 1. Temporarily ignore the 4 and the negative 2. Those are going to be the answers. But how do we get those answers? All right, so from what we did yesterday, start off with a over 2x plus 1 plus b over x plus 1. Now you need your common denominator. So this pen, you need to have x plus 1 over x plus 1. And what has to be behind this pen? 2x plus 1 over 2x plus 1. That's to get my common denominator. So my common denominator is 2x plus 1, x plus 1. Multiply out all the top. Ax plus a plus 2bx plus b. Now I gather the x's together. So these two have x, right? Factor out that x, a plus 2bx. And then the non-x's, everything that doesn't have an x, these two, a plus b. Okay. So this thing is equivalent to this thing. And that's now where I compare it back to the original. Okay. And you can see now that's the reason why the 2, I need to write as 0x plus 2. Because I want to make this fraction equal to this fraction. The denominators are already the same. So how can I get the numerators to be the same? Well, the coefficient of x has to be 0, and the constant has to be 2. So here are my 2 equations and 2 unknowns. A plus 2b better be 0 from right here. A plus b better be 2. So here we are. A plus 2b equals 0. This coefficient of x has to be 0. And a plus b has to be 2. And I have 2 equations and 2 unknowns. Okay, and the easiest way to do this is to subtract. I'll subtract a minus a is nothing. 2b minus b is b. 2 minus 2 is negative 2. So b is negative 2. And plug back in here, that means a is 4. So that's where I get the 4 and a negative 2 from. So now I know that my original fraction, the rational expression, is 4 over that minus 2 over that, and that's an easy integral. So my integral is now from 0 to 1, 4 over 2x plus 1 minus 2 over x plus 1. All right, so it's 4 times ln absolute 2x plus 1 times a half by the chain rule in reverse. Remember, if I differentiate right here, you would multiply by 2. So since I'm integrating, I divide by 2 and multiply by half. So it's 4 times a half, which changes to 2. Minus 2 natural log absolute value of x plus 1. No need to worry about a coefficient here because the derivative of x plus 1 is 1. Okay, and I'm going from 0 to 1. Okay, plug in 1, 2 ln 3 minus 2 ln 2 minus parentheses, plug in 0. This becomes ln 1, which is 0. That becomes ln 1, which is also 0. So I just have 2 ln 3 minus 2 ln 2. Okay, I'll accept this, but you could get more fancy and clean it up more. For instance, I can factor out the 2. 2 times ln 3 minus ln 2. ln of 3 minus ln 2 is ln of the quotient, 2 ln 3 over 2. And you can get even more fancy by bringing the 2 back up. That's one of the properties of logs. 2 can climb up back stairs. So the absolute simplest form is natural log of 9/4. But again, if you want to leave it right here, that's okay. Accept that. Okay, so this is the idea of partial fractions we have here. All right, now, next one's a little harder, 17. Let's see what they have there. The bottom has y plus 2, y minus 3. 4y squared minus 7y minus 12. Okay, that really doesn't matter that much for now. So there's going to be 3 things here. So the ones that I've done so far, there are 2 factors in the denominator. Right, and the one I showed you yesterday was likewise. Now there's a y plus 2, y minus 3. So I have to break it down into a over y plus b over y plus 2 plus c over y minus 3. So that's a lot more work. Again, temporarily ignore this. This comes out to be the answer. But if you stop and think about it, it doesn't bother me what the numbers are. They can be real bad numbers. They're still constants. Constant, 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 right? So it's going to be a constant times ln, constant ln, constant ln, right? So to me, the hard part is really just all this messy algebra. Okay, now, think back in algebra, if you were to get a common denominator. What's the common denominator? All this stuff. So for each of these 3 fractions, you ask yourself, what do you need to build it up to here, right? Well, it's the ones that they don't have. So this fraction already has a y. So it needs these 2 guys, y plus 2, y minus 3, right? Y plus 2 is going to need y times y minus 3. And the last fraction, y minus 3, is going to need y times y plus 2. Okay. And unfortunately, I have to go up and down this. So this one needs y plus 2, y minus 3. Y plus 2, y minus 3. The middle fraction, b over y plus 2. So it needs these 2, y times y minus 3, y minus 3. And of course, whatever you do in the bottom, do the same thing on top. And c over y minus 3. Well, it needs y times y plus 2. Y times y plus 2, right? That's in order for me to get my common denominator. So now all 3 of these fractions have the same denominator, right? Y plus 2, y minus 3. And then, and only then, am I allowed to combine the numerator. Okay. So it looks quite messy. I'm going to leave alone the a, the b, and the c. So multiply this out with FOIL, y squared minus y minus 6. I trust you can all do that. That's y squared minus 3y, and that's y squared plus 2y. Okay. This is quite long. This is quite long to multiply all out. Okay. So I could multiply that all out, but I'm going to trust your algebra ability. You're all taking Calc 2, which means your algebra is all very good. I'm going to break it down into y squared, y, and constant. And by constant, I mean it doesn't have any y. Okay, so let's look at all the y squared. There's going to be ay squared, by squared, cy squared. Here it is, right? I got lazy, but frankly, I think you would get lazy too. I don't feel like writing this all out and then go back and factorize. Yeah, I can tell, you know, so, oh yeah, there's an ay squared, by squared, cy squared. Here it is. Of course, if you were in my Algebra 1 class, I wouldn't go that fast, but you're in Calc 2, you should be able to follow the algebra, right? Ay squared, by squared, cy squared. So a plus b plus c, y squared. Do the same thing for y. So y is going to be negative ay, right? Minus 3by plus 2cy. Okay, one more time. Negative ay minus 3by plus 2cy. So I factor out the y, negative a minus 3b plus 2c. Okay, and double check. Negative ay, there it is. 3by, oh, sorry, minus 3by. There it is. And 2 plus 2cy. And then constant, something that doesn't have any y, there's only one thing, negative 6a. Nothing here is going to be void of a y. There's going to be some y here and some y here. So that's pretty much everything. And a quick inventory. 1, 2, 3, 4, 5, 6, 7 terms. 1, 2, 3, 4, 5, 6, 7. So there it is. So I got blah, 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 y squared, blah, 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 y, and blah, 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 just constant. And now I look back at what I originally had, 4y squared minus 7y minus 12. Okay, so just like before, that means all of this better be 4. The y coefficient better be negative 7, and the constant better be negative 12. So a plus b plus c equals 4. Negative a minus bb plus 2c equals negative 7. And negative 6a equals negative 12. This time I have 3 equations and 3 unknowns, which you might recall from your algebra, you can solve, right? So the problems that I did so far were 2 equations and 2 unknowns. This has 3 equations and 3 unknowns. And just for your curiosity, if I had 4 factors in the bottom, you would have 4 equations and 4 unknowns. If you have 5 of them, you have 5 equations and 5 unknowns. I'm not going to give you anything that big. I mean, this is already big enough, but that was at least the principle behind it. Okay, so 3 equations, 3 unknowns. Okay, the easiest one to solve is the bottom one. That's easy. That means negative 6a equals negative 12 means a is equal to 2, right? So a is done, that's 2. Put 2 back there and 2 back there. And then if I subtract 2 from the top equation, I get b plus c equals 2. And put a 2 here, you get a negative 2. So if I add 2, get negative 3b plus 2c equals a negative 5. So now I have 2 equations and 2 unknowns. Let's see, what did I do? I multiplied the top equation by 3. So that gives me 3b plus 3c equals 6. Leave this one alone, negative 3b plus 2c equals negative 5. Add them up, 5c equals 1. C is 1/5. Yes, it's a fraction. And then what did I do? I know that b plus c is 2. So put c as 1/5 here. So b is 2 minus 1/5, which is 9/5. So I found my a, b, and c to be 2, 9/5, and 1/5. So my original integral, which has this rational expression, this big polynomials over another polynomial stuff, I'll write it as 2 over y plus 9/5 over y plus 2 plus 1/5 over y minus 3, and they're all just going to be ln's. Okay. And there it is. 2 over y, 9/5. Don't worry about the 9/5. It's just a constant. I don't care if it was square root of 2 over 2 or pi divided by e or whatever, it's still going to be okay. It's a constant. Then 1/5 over y minus 3. Okay, so all of these are ln's. 2 ln absolute y, 9/5 ln absolute y plus 2, plus 1/5 absolute y minus 3, from 1 to 2. Okay, plug in 2. 2 ln absolute value of 2 is 2. 9/5 ln absolute value of 4 is 4. 1/5 ln absolute 2 minus 3. 2 minus 3 is -1, whose absolute value is 1. And then I quickly cross this out because ln of 1 is 0. Minus, plug in 1. 2 ln absolute value of 1 is 1. ln of 1 is 0. That's gone. Plug in 1 here. 9/5 ln absolute value of 3 is 3. 1/5 ln absolute value of 1 minus 3. 1 minus 3 is -2, whose absolute value is 2. So absolute value is critical. And by the way, side note, it's especially important, you can see in this particular problem that you need the absolute value, right? So some of you are leaving off the absolute value when you do the antiderivative. That's a little bit too sloppy, okay? So remember, the integral of 1 over x is not just ln x, it's ln absolute value of x. And actually, if you put parentheses, then you would got stuck if you plug in 1 or 2, right? Because then you'd be taking the ln of a negative, and you're not allowed to take the ln of a negative. Okay? But if there's a bar there, then you're good. So that becomes a positive, even though it was originally -1, right? And that was also originally -2, but the absolute value makes it 2. Okay, so now just throw everything together. 2 ln 2 plus 9/5. I wrote this as ln 2 squared because I'm going to combine it with all the others. Minus 9/5 ln 3 minus 1/5 ln 2. Okay, then what did I do? 2 is allowed to come down. 2 times 9/5 is 18/5. Okay, then I combine that one, and that one. Okay, just combine the coefficients. This is 10 over 5 plus 18 over 5 minus 1 over 5. So 27 over 5 natural log of 2 minus 9/5 natural log of 3. And I think I'll just leave it like that for the final answer. Okay. All right, so that's that. We're actually going to take a pause now from doing these kind of problems. You may have noticed I haven't shown you how to do any of 1 through 6. So what's that all about? Okay. So the problems that we've done are actually the quote unquote easiest. And the so-called easiest is the more than likely kind of problem I would give you on the exam. Okay. These problems could actually get harder. There's 4 separate cases that I need for you to consider. And again, if you want to put these on your cheat sheet, you may. So let me go over those now in the text. The text calls them case 1, 2, 3, and 4. Okay. So on page 494 is case 1. (496) is case 2. So far, we've been doing case 1, the easiest case scenario. Okay, and don't get too scared, but we've really only been doing the easiest problems. Okay, and I'm only going to give you most likely the easiest ones. The harder ones, like case 2, 3, and 4, are probably just going to be a setup, which is like problems 1 through 6, which I'll show you shortly. Okay, case 3 is on 497. And case 4 is 499. Okay, so what are these cases? Okay, again, you're welcome to put this on your cheat sheet. 494, we've been doing case 1. The denominator, so right now we're only looking at the denominator. We don't really care about the numerator. The denominator is a product of distinct linear factors. So we only have linear expressions, ax plus b, in the denominator, and distinct meaning there's no repetition. Like the ones we've been doing, a1 divided by a1 x plus b1, a2 divided by a2x plus b2, and so on. Okay. And by the way, if you have to do polynomial long division to get the numerator to be a smaller degree than the denominator, then do so. Okay, so the first thing you might have to do is polynomial long division. Okay, so if this is third degree, this needs to be second degree or lower. If this is fourth degree, the numerator should be third degree or lower. And if it isn't, you can always do polynomial long division to make it that way. Okay, that was sort of like the first problem that I did, which I think was 7. Right? Yeah. Remember we did polynomial long division of that. And after you did long division, it was pretty straightforward to integrate. All right, so case 1, the easiest case scenario, and the only one where I'm more than likely to give you on the exam, looks like this. This kind of looks like the one I just did, right? So blah, blah, blah of x, 2x minus 1, x plus 2. It looks like they factored the denominator. All right, so x, 2x minus 1, x plus 2, a, b, c. Just like the one that we did, right? All right, and yes, I'm not likely to ask you case 2, 3, or 4 in its entirety, but lest you think, oh, he's not going to test me on it, I don't have to think about it. No, I might ask you just for the setup, which would be like problems 1 through 6. Okay, they're too long to do in its entirety, right? But I might just ask you for the setup. Right, so case 1, so-called easiest case scenario, the denominator only has linear factors. Okay, so now what makes it harder? Case 2, page 496. Q of x, Q means quotient, denominator, is a product of linear factors, some of which are repeated. You might have a repeated linear factor. So here's an example of a repeated linear factor. X squared, x minus 1 cubed. All right? So it's not just x times x minus 1. If it's just x times x minus 1, we know what to do with that. X squared, x minus 1 cubed. Okay? So look at what they do. And again, you can put this on your cheat sheet if you want. All right? You see x squared, x squared. X minus 1 cubed. X minus 1, x minus 1 squared, x minus 1 cubed, right? So if you have a repeated factor, you start at the bottom and work your way up. So 1, 2, x minus 1 cubed, 1, 2, 3. So suppose you have x to the 7th, then you need x squared, x cubed, x to the 4th, x to the 5th, x to the 6th, x to the 7th. See how it goes? All the way at the bottom, all the way up. Okay, and yeah, this takes way too long to do the whole thing. So I would never make you do the entire problem for something like that. And then just go A, B, C, D, E. And you can clearly see how messy this would be for the algebra to get a common denominator. So this is what I might ask you on the test, is not to finish this, but just to set it up. Okay, so again, one more time, notice it's x squared, right? So over here, you go x squared. This is x minus 1 cubed. So I'm going to go x minus 1 squared, x minus 1 cubed. Okay. Suppose I have x minus 3 to the 5th power. Then I have x minus 3 squared, x minus 3 cubed, 4th, 5th. Right, so you start at the bottom and work your way up until you get the exponent that you have. Okay. All right, so here's an example of which I'm not going to do the whole thing. Find this integral. Okay, first, you notice that this is 4th degree. This is 3rd degree, right? So I'm first going to do long division. I got to make the numerator smaller degree than denominator. In other words, get it to something like this. Okay, the bottom's 3rd degree. So the numerator has to be 2nd degree or lower. Right? So they did the long division. Well, I guess they didn't show it, but you could do it, do the long division stuff, right? Go like that. Inside is the x to the fourth stuff. Outside is x cubed stuff, blah, 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 blah. And I guess this is what it comes out to be. X plus 1 plus all that stuff. Remember, we're integrating. So if I replace the original integral with all this mess, x is easy to integrate, 1 is easy to integrate, and then I got to do my partial fractions on this stuff. All right, so they divided this out. And if you divide this out, remember you did some of that in pre-calc, hopefully, factorize this, x minus 1, x squared minus 1, which is x minus 1, x minus 1, x plus 1, or x minus 1 squared, x plus 1. Okay, so finally, the denominator is factored. This stuff here is x minus 1 squared, x plus 1. So we have linear factors, but some of which are repeated. So look at what they do. For x over x minus 1 squared, x plus 1. Okay, x plus 1 is not repeated. Just put it. But look at what they did here, right? This is x minus 1 squared. So to work out x minus 1 squared, put x minus 1 squared, and then just a, b, c on top. And there we go. Okay. They actually went ahead and started working all it out. It's really long, but it's possible. By the way, I just mentioned quickly, when you integrate, this is going to be an ln. This is going to be an ln. This is not an ln. Right? This one you treat as x minus 1 to the negative 2 power, bring it upstairs, x minus 1 to the negative 2, and then just do your power rule. Okay, so this is what you do if you have a repeated linear factor. Case 3. Irreducible quadratic factors, none of which is repeated. Irreducible quadratic. The quadratic cannot be factored. And one thing about these is we could factor it, right? This is a cubic, but we got it a factor. We factored down to this, I guess, right? Now we're tackling the case of, well, what happens if you have factors in the denominator which you can't break down anymore? So Q of X, quotient, denominator, contains irreducible quadratic factors, none of which is repeated. Here's an example. Well, I've already shown you the answer, but pretend we don't see it. X over X minus 2, X squared plus 1, X squared plus 4. Okay. These two are called irreducible quadratic factors. You can't factor this, right? At least among the real numbers. Now, if this were x squared minus 1, right, then you say, oh yeah, factor into x plus 1, x minus 1. And likewise, if this was x squared minus 4, it would not be considered an irreducible quadratic. It's reducible. X squared minus 4 can be reduced to x plus 2, x minus 2, right? But I cannot go any farther with that. So what should I do? Okay, this one's a linear factor. So that's just like before, a over x minus 2. These two, however, cannot be broken down further. X squared plus 1, x squared plus 4. So what's the rule this time? Take a look at what they do. X squared plus 1, bx plus c. X squared plus 4, dx plus e. So if this is second degree, this is first degree, linear. Second degree, first degree. This is already linear, so you just put a constant. So in general, the numerator is 1 degree less than the denominator. So this is first degree, so I make this 0 degree, which means a constant. This is second degree, make this first degree. This is second degree, make this first degree. See that? Okay, so one more time, x minus 2, linear. X squared plus 1, irreducible quadratic. I cannot break it down. X squared plus 4, irreducible quadratic. All right, then I go, all right, x minus 2, x squared plus 1, x squared plus 4. X minus 2, just put an a on top like before. But look at what happens for each of these, right? If you have an irreducible quadratic, cannot break it down, you put a linear expression on top, bx plus c. And likewise, x squared plus 4 is another irreducible quadratic, make it dx plus e. Okay. And to integrate each of these are like inverse tangent. So if you want to put this on your cheat sheet, you may. You have x squared plus 1 or x squared plus 4. The way to integrate those is make them into inverse tangents. So here's the setup again. Most likely, I won't have you do the entire thing, but I might. And I think there's some homework problems where you do, but for a 1-hour exam, you're not going to have enough time. I might just say set it up. Okay, so blah, blah, blah. Let's see, second degree, third degree, that works. So factor x times x squared plus 4. Okay, so x is linear, but x squared plus 4, irreducible quadratic. So look at what they do. Break it up into x squared plus 4. X gets an a on top. Look at what happens over here. X squared plus 4 gets a bx plus c on top. Okay, and then, yeah, they go through all of this stuff. It gets lengthy, but there you go. That's an ln. This is going to be one of your inverse tangent ones. Okay. All right, so that's what happens if I have an irreducible quadratic. And finally, case 4, it's kind of a combination of case 2 and 3. Repeated irreducible quadratic. You have an irreducible quadratic and it's repeated. Well, they give you the root here, but I think it's better to just show you an example. And again, you can put this example on your cheat sheet. Write out the form of the partial fraction decomposition of the function. Blah, blah, blah. Okay, again, you don't care about the top as long as the degree of the numerator is smaller than the degree of the denominator, right? And it is. The numerator is third degree. The bottom is way above that. Okay, so let's look at what we got. X, linear. X minus 1, linear. X squared plus x plus 1 is an irreducible quadratic. You can't factor that. You can try it, or if you do the quadratic formula, you'll end up with the square root of the negative. X squared plus 1 cubed, irreducible quadratic, repeated. Repeated irreducible quadratic factor. Okay, so let's look at what they do. Okay, x, normal. X minus 1, normal. A on top, B on top. This one, x squared plus x plus 1, irreducible quadratic. Cannot break it down. Cx plus d, linear. And now, repeated irreducible quadratic. Irreducible quadratic, repeated. Okay. So this is where I kind of combine part 2 and 3. X squared plus 1 cubed, I'm going to put x squared plus 1, x squared plus 1 squared, x squared plus 1 cubed. And look what they got on top. Ex plus f, gx plus h, ix plus g. Theoretically, you never run out of letters. Okay, even if it goes all the way to z, you can start using Greek alphabet or any other alphabet or whatever. Okay, so just like the section or case 2, if there's a repetition, x squared plus 1 cubed, then I say, okay, x squared plus 1, x squared plus 1 squared, x squared plus 1 cubed. And since these are irreducible quadratics, linear, linear, linear. So ex plus f, gx plus h, ix plus j. Kind of hard to say all that stuff. And that's the way it works. Okay, so one more time for this one. X, linear, easy. X, put an a on top. X minus 1, easy, linear. B on top. X squared plus X plus 1, irreducible quadratic. So I need a linear expression on top, CX plus D. X squared plus 1 cubed means X squared plus 1, X squared plus 1 squared, X squared plus 1 cubed. And then linear expressions, EX plus F, GX plus H, IX plus J. And now finally, we're ready to tackle 1 through 6, where it says write out the form of the partial fraction decomposition. Do not determine the numerical values of the coefficients. Okay, so this is something I can certainly ask you on the test, where it would be too long to actually find the coefficients, but at least give the setup. Okay. Let me try to show you a couple of those, and maybe that's about it for today. Okay, and unfortunately, I have to give you starred problems that I've already done. So 1A star, I notice it's not the same as in our book, but it's essentially done the same way. 1 plus 6x over 4x minus 3, 2x plus 5. This is the easiest case scenario, case 1. Only linear factors, no repetition. So 4x minus 3, 2x plus 5, A, B. Nothing can be easier. Again, that's not our 1A, so it's 1A star, but it works in a similar fashion. 1B star, 10 over 5x squared minus 2x cubed. Okay, factor out the x squared, 10 over x squared, 5 minus 2x. Okay, so this is linear repeated. So what am I going to do with x squared? X squared. If I had x to the 4th, I go x squared, x cubed, x to the 4th. If I had x to the 10th, I go x squared, x cubed, x to the 4, 5, 6, 7, 8, 9, 10. Then how about this one? No repetition, 5 minus 2x, and then just A, B, C. Okay, then I'm going to show you 3A star, x to the 4th plus 1, x to the 5th plus 4x cubed. All right, so factor the denominator into x cubed, x squared plus 4. All right, so what do I have here? I have a repeated linear expression, x cubed, and an irreducible quadratic. All right, so what am I going to do for x cubed? X squared, x cubed, A, B, C. But x squared plus 4 is an irreducible quadratic, which means what do I have to put on top? Not just D, dx plus E. Okay. So that's the way it goes. So that's how 1 through 5 works. Now, for some of them, you're going to have to divide through first. Okay, so like 5A, I'm noticing. 5A, the first thing you want to do is the polynomial long division. Do the long division to break it down into something that does not have a squared or above in the numerator. So get it down to be a linear. And then, of course, after that, you factor in x plus 2x minus 2. Okay. All right. Okay, that was about all I was going to do for today. So let me stop the share and see if anybody else has anything. Whoops. I messed up there. Okay, any questions? Otherwise, we'll call it quits for today. Check the chat. All right, see nothing and hear nothing. So that's it. Okay, folks, have a good day, and we'll see you next time. Okay, bye, everybody.
All right, take care, Professor.
Thank you. Bye.